Hello, today I am going to drive the average velocity profile for a liquid falling through a film. So let's start. So first of all, I would like to write the velocity distribution profile which we have already derived. It was Vz equal to rho g cos of theta cos of beta del square over 2 mu multiply by 1 minus x over del whole ka square bracket. This was the velocity distribution across the falling film. Now most of the students face difficulty while calculating the average velocity. So in this video I'll tell you how to calculate this average velocity. Let us consider a shell having flow in z direction and depth in x direction, whereas is width in y direction. So if I make it simple, it would look like just like this. This is our x direction, this is our z direction, and this is our y direction. So we represent average velocity with these symbols. So we put it equal to derivatives from 0 to w, which represents the y direction, from 0 to delta, which represents the x direction, dx and dy, whereas here it comes the velocity distribution divided by the 0 to w, 0 to del, dx and dy. We know that here our velocity profile is not depending on the y direction, so derivative 0 to w with dy will come out of this equation and will be cancelled out like this. So we will take out this dy del 0 to w into dy and separate it from del 0 to limits 0 to del vz dx and over 0 integral 0 to w dy over integral 0 to del into del x. So this is constant, therefore it will be cancel out. Now we will just simply uh, solve the denominator. So here we go. So it will, as you know that there is a constant, so when we put the limits, so it would just simply give us delta. We will take this delta out and place this rest of the equation like this. Now we know that this Vz was our velocity distribution profile, which is written over here. Let's name it as A. So what we do next, we'll just simply put our velocity distribution profile equation A at Vz place. So let's write it. 1 over delta 0 to delta, so rho g cos of beta into del square over 2 viscosity into 1 minus x over del whole square and brackets into dz. Now as you know that we have placed our values in the place of Vz. Now just here we have to be very conscious that these terms, density, gravity, cos of beta, del square over 2, viscosity, these are constant terms. So we will take these terms out of this integral. Here I have just taken the constant terms out of this. Here we can cancel this delta with delta square. So we are left with only one delta outside. So what we do is just simply write this equation again rho g cos of beta into delta over 2 viscosity into 0 integral with limits 0 to delta and function 1 minus x over delta whole square dx. So now we'll just simply take this part of the equation and integrate it with the upper and lower limits. So what we do, we just take this integral and solve it separately. We know from the basics, from the metric FSC or metric grade, like we just take the integral with individual values. Like I have taken integral with its limit for 1, and similarly for the other x over delta whole square dx. Here you know that integral of constant is the we have here upper limit, so this will come instead of 1, so it would become delta, whereas in this term we know that this is x over delta whole square, so this is independent term, delta is independent term, so it will come out of this integral, so it will become 1 over delta square. We are only left with integral with a lower limit 0 and upper limit delta, and inside we have x square dx. We'll just solve this, whereas taking this out, writing it again, delta minus 1 over delta square. So we know that when we do integration, we have formula, we are all know that x n plus 1 over n plus 1 with limits 0 to delta. So delta 1 minus 1 over delta square with x with power x cube over 3 with limits 0 to delta. Now we will apply these limits and see what we'll get. Delta 1 minus delta minus 1 over delta square. Let's write 3 with this, and here we go. This x, this upper limit delta cube minus lower limit 0 cube, as you know that whatever the power of 0 is always 0, so delta minus, here we are left with delta cube over 3 delta square, so this delta square term will be cancelled out with this cube, so here we go, we are left with delta minus delta over 3, so we just take LCM, and 3 delta minus delta over 3, this will give us 2 delta over 3. So we'll just replace this 2 delta over 3 term in this whole integral, so it would make our equation very simple. So I'm writing it here. So this is rho g cos of beta over 2 mu into delta multiplied by 2 delta over 3. So this 2 will cancel out with this 2 in the denominator, and we have this rho g cos of beta delta square. These delta and this delta will become delta square over 3 viscosity. So this is the average velocity which we were looking for. So this is the equation of average velocity, so we have found it.